We are diving immediately into CoV, chain of view prompting for spatial reasoning. Okay, let's unpack this for you. The core challenge that CoV is tackling is a really fundamental bottleneck in embodied question answering, EQA, right?
Right, especially in 3D environments.
Exactly. So right now, these models are just crippled because they rely on these fixed, finite sets of input views. So if the answer to your question is, say, occluded, or if it's spread out across a scene, like around a corner or something, the model just can't get the information. It completely stonewalls any kind of complex spatial reasoning.
And this is exactly where the chain of view prompting framework comes in. And this is the key phrase, a training-free test-time reasoning method.
That's huge.
It's a game changer. It basically transforms these standard vision language models, these VLMs, into what you could call active viewpoint reasoners.
And the mechanism is just so elegant. It feels like how a person would actually figure something out in a new room. It's this two-stage coarse-to-fine exploration.
Yeah.
So first, it sifts through the data, right? It picks out a few key anchor views. And then, this is the magic, it starts dynamically adjusting the camera. It's rotating, it's moving, until it has enough visual evidence to ground the answer.
And the impact isn't small. We're talking about an average improvement of over 11.5% on the OpenEQA benchmark.
Yeah.
That number alone shows you just how powerful this test time scaling capability is.
Okay, so that's the 1-minute summary, but let's really get into the philosophy behind this.
Let's do it.
This whole thing is really about a conceptual shift, isn't it? It's moving from being a passive observer to being an active explorer.
Absolutely. And for anyone working in robotics or autonomous systems, this is the next logical step. That's a non-negotiable one.
For sure. If we want embodied AI to actually get out of simulations and into the real world, robot navigation, manipulation, it has to be able to handle things being hidden.
That's the EQA challenge right there. Conventional models, they treat the world like a slideshow. They get a fixed set of images and just try to guess.
They can't ask for more data.
Exactly. And the paper's example is perfect. Where can I get some pop drinks? A passive VLM, if it can't see the fridge in the initial pictures, it just fails. It has no idea.
It needs that semantic leap, right?
Yeah.
To know that pop drinks means find a refrigerator, which might be behind a wall, a passive model can't do that. It just hits a wall.
And this is where that training-free part gets really interesting for the whole industry. CoV doesn't just look at frames. It leverages the underlying 3D scene representation, the point cloud, the mesh, to explore this open-ended view space.
So it doesn't need to be retrained on a million different how to explore examples.
Not at all. And that's massive because it means you can apply it right away, and it cuts down so much on computational cost. We're just leveraging the reasoning power that's already in these big VLMs, your Geminis, your Quins, and giving them a new tool.
We're making the model work harder at inference time, not training time.
Precisely. And that efficiency really starts with that two-stage structure, coarse-to-fine.
Right. So stage 1 is the triage, and stage 2 is the active investigation. Let's start with stage 1, the coarse-grained view selection. This is all about cutting down the noise, yeah.
100%. I mean, your initial input, call it $5, it could be a massive video or hundreds of frames. Most of that is just redundant.
Yeah, just slightly different angles of the same boring wall.
Exactly. So the goal here is to filter that down to a much smaller subset of keyframes, let's call it $5, where the number of views is just a tiny fraction of what you started with.
So how does it actually decide what's junk and what's useful?
It's pretty clever. It uses the VLM itself as a view selection agent, guided by a prompt.
So it's prompting the VLM to do the filtering.
Yes. And the prompt gives it 3 main jobs. First is target localization. It looks at the question and figures out the key objects or regions it needs to see.
Okay, and second?
Second is the view selection logic. It picks views based on clarity, minimal occlusion, or whether it captures the spatial relationship between things. And third is redundancy reduction. It actively tries to pick views from different angles.
Now, here's something that jumped out at me. The paper talks about giving the agent a bird's-eye view of the whole scene to start. Doesn't that kind of cheat the whole embodied AI idea? A real robot doesn't start with a perfect map.
That is a very sharp point. And I think the researchers would agree it's not pure embodiment. But here, the bird's eye view isn't the answer key. It's more like a facilitator.
A way to get its bearings.
Exactly. It helps the agent understand the overall layout. So when it starts its local exploration in stage 2, the anchor views it chose back in stage 1 actually make sense. It stops it from just picking 30 views of the same corner.
That makes sense. It's a practical trade-off to focus the reasoning budget. And the data backs this up, doesn't it?
Absolutely. The ablation study was clear. If you take away this coarse grain stage, performance tanks, they saw an average drop of about 4.5%.
So it's proof that a little bit of strategic thinking up front saves you from getting lost down the line.
It's essential. It keeps the model from wandering off before it even starts moving.
Okay, so once we have those key starting points, we get to the really dynamic part. Stage 2, the fine-grained view adjustment. This is the iterative action reasoning chain.
This is the heart of it, yeah. The CoV agent is basically in a planning loop. At each step, the VLM looks at what it sees, looks at the question, and asks, what am I still missing?
And based on that gap, it generates an action instruction.
In natural language, yes. It's like the VLM is thinking out loud, explaining why it needs to move.
And that instruction, that thought, gets turned into an actual physical change. It's mapped to an SE3 transformation matrix. For those who aren't deep in robotics, that's just the math that tells the camera exactly how to move and rotate in 3D space.
Right. It's the command that updates the camera pose, and that gives you a totally new viewpoint. But crucially, that new view gets added back into the agent's memory.
So it builds a cumulative history, a chain of views.
That's where the name comes from. It remembers where it looked, why it looked there, and what it saw.
So what's in its toolkit? What moves can it actually make?
The action space is pretty comprehensive. It's broken into 3 types. First, you've got your translational actions.
So move forward, backward, left, right, up, down.
Yep. Fixed little steps, great for getting a closer look at something. Then you have rotational actions.
Yeah, pitch and roll. So looking left and right, up and down, and tilting.
All the ways you'd move your head to get a better angle. And the third category is maybe the most strategic, view switch actions.
So it can jump back?
It can. If it gets too deep in one spot and realizes the answer is related to something it saw earlier, it can just instantly snap back to any of those initial anchor views from stage 1. It keeps it from getting lost.
Let's walk through that where is the mirror example. So stage 1 picks an initial view, $1, but maybe the mirror is kind of in shadow.
Right. So the chain starts. The VLM thinks, I need a clearer view, and generates action 1, right rotation plus 10. The reasoning is something like, I need to see its placement on that cabinet better.
The simulator rotates, gives it a new picture. Now it wants to see the frame up close.
So it thinks again. Action 2, forward movement plus 2. Reasoning. I'm moving closer to confirm the material of the frame.
And maybe after that, it needs to see where it is relative to the door.
Exactly. So you get action 3, left rotation plus 15, just to confirm its position in the room.
It's so powerful because it's so logical, and it only stops when it's gathered enough info or hits a step limit. I like that it has to enter a verification phase before answering.
Right. It forces it to ground the answer in that chain of evidence, and the numbers show it works.
Let's talk about those numbers, the OpenEQA results. That average improvement of 11.56% is pretty staggering.
It is, and that's across 4 different major VLMs. It even peaked at over 13.5% on Qwen 3 VL Flash. For a strategy you just apply at inference time, those are huge gains.
And it holds up on other benchmarks too, right? This is not a one-trick pony. On ScanQA, you mentioned it got state-of-the-art with 116 CIDR.
Yeah, and for those who don't live and breathe these metrics, CIDR basically measures how human-like the generated description is. A score of 116 means it's not just finding the object, it's describing its location with real nuance.
And on Sketty 3D.
Also state-of-the-art with 51.1 EM at 1. Exact match. It's just getting the answer right. It proves the model is robustly understanding the scene.
But I think the most crucial finding, the one that points to the future, is that test time scaling verification.
Oh, for sure. This is where they experimented by forcing the VLM to take more steps, even if it thought it was done.
So they made it be more curious, basically.
You could say that. And the result was clear. Forcing a bigger action budget gave them another average improvement of 2.5%, peaking at almost 4% on a Gemini model.
It's not a huge number, but the implication is massive.
Yeah.
It means that deeper reasoning inherently improves accuracy.
Exactly. Even though most questions only need 1 to 3 steps, forcing the model to look more deeply helps it find subtle context it might have missed. It's a huge signpost for where this research is heading.
It really is a conceptual shift. It's not just about what the model sees, but how it decides to see and how it remembers.
It's memory tied directly to active search.
But the paper is also good about flagging the limitations. It's not a perfect solution for every environment.
No, not at all. For example, in really dynamic or super cluttered spaces, this coarse-to-fine approach could really struggle. If things are moving around while the agent is exploring, its chain of views gets outdated fast.
And there's a risk if the exploration goes on for too long, right? The trajectory length.
Yes. Too many steps can actually introduce noise or even cause the VLM to hallucinate. You're feeding it more and more data, and at some point that can become confusing instead of helpful.
And the most fundamental weakness, which we touched on earlier, is that the whole thing lives or dies by that initial view selection.
Garbage in, garbage out. If stage 1 messes up and picks bad starting points, stage 2 is already at a massive disadvantage, no matter how clever it is.
So future work seems pretty clear. It's about making that initial selection more robust and building adaptive reasoning that can handle more complex, real-world messiness.
I think so. But what code gives us is this incredibly solid model-agnostic blueprint. It proves you can unlock deep spatial reasoning at inference time just by giving a VLM the power to look around.
It proves that the best data isn't always what you start with. It's the data you choose to go find.
Well said.
So that brings us to our final thought for you to chew on, and it builds right off that test time scaling result. We now have clear evidence that forcing a model to explore, more increasing its action budget, yields better accuracy. So how should researchers balance the very real computational cost of more exploration steps against that marginal gain in performance?
That's the billion-dollar question.
It is. It's the core trade-off between reasoning depth and resource efficiency. And figuring that out is going to define the next generation of truly generalist embodied agents.